everywhere below the liquid curve. In between, where we have this two-phase region, the situation must look something like this. We have a liquid curve here, the alpha curve here. There's a spurious L up there. So that liquid is stable on this side, alpha is stable on that side. Here's a common tangent. We have a two-phase region between them. As the lowering temperature, as the alpha curve moves through the liquid curve, it first touches over on this side right here, generates a two-phase region. As the alpha moves through the liquid curve, that two-phase region just kind of moves in this direction until finally the alpha cuts all the way below the liquid curve and ends up here. And the net effect is to generate a phase diagram that looks like this. There are a couple of other forms of solid solution diagram they have, but this is the simplest. This is the one we're worried about. It appears at the melting point of the high temperature phase. It's eliminated, in this case, the melting point of the low temperature phase and produces a lens-shaped two-phase region in between. Now, what might be some uses of that phase diagram? Well, let's consider what happens as we solidify a solid solution. So we're going to start up here in the liquid phase at this composition that I've shown here in the left-hand plot in the figure here. And I'm now going to cool at that constant composition. As I cool, nothing happens until I hit the liquid, what's called the liquidus curve, the upper end of this two-phase region right here. As soon as I do that, some liquid's going to start to form. Well, how much and what composition? Well, let's just go to the temperature at which I cooled it. Let's say it's right here. When I get to this point, the liquid will have composition XL, the solid will have composition X alpha, and the mole and the fractions will be given by the lever rule. So when I get to this temperature, there's a bit more alpha phase than there is liquid phase. And of course, the alpha has a composition that's much richer in solute than the liquid is. When I first come into this region, I get a very tiny bit of liquid, which is going to, a very tiny bit of alpha, which is going to have this composition over here. As I come down through the two-phase region, what happens is the liquid composition starts evolving this way. The liquid becomes leaner in alpha. The alpha phase becomes leaner in solute as well. This composition is evolving along this line. But the fraction of the alpha is increasing until finally I get to here. Now I have 100% alpha and its composition is back to the overall composition of the solution. But note that as I come through the two-phase region, I get a composition deviation, which can be rather large. The composition of the alpha can be quite different from the composition of the liquid, and the lever rule gives you the mole fractions. Now, the ways I can use that. One of the, I think I mentioned way back at the beginning when I was first introducing this course that in engineering, very often, well, maybe I didn't say it, let me say it now. If you look at the history of engineering, very often there are enabling technologies. If you look at great inventions that happen, I'll give you an example a couple of weeks ago. Take the automobile. The automobile would not exist in its present form, or would not have come into being in its present form, if someone had not invented the pneumatic tire, which went back to Goodyear and vulcanization. The reason was to have off-track vehicles, you need a way of making tires that can survive off-track operations. And we could be driving on tank treads, I suppose, but that wouldn't make for great, kind of chew up the landscape a bit. Someone invented the rubber tire, and as a consequence of Goodyear inventing vulcanization of the rubber tire, we have an automobile industry. Semiconductors. You talk about the semiconductor revolution, and everybody points to Bardeen and Shockley back at Bell Labs in 1948 coming up with the transistor. Huge breakthrough, revolutionized the world. Took a while, but did revolutionize the world. If you go back and pick up a solid-state physics book, like Fred Seitz' famous classic book, written in the 1930s, and go to the section on semiconductors, you will see, if you read between the lines, he can describe a transistor. Nobody made it. Why not? They were missing the enabling technology. As you'll see when we get to semiconductors, in order to make a functioning semiconducting device, you need very pure starting materials so that you can control their conductivity and the type of conductivity by adding active dopants to them. So no transistor was going to be invented until somebody figured out how to make a really pure starting material in a very simple way. The guy who did that in late 1947 was Bill Phan, kind of a pudgy little fellow. He used to spend half his year out here when I came here in the early 1970s. He produced a process called zone melting, which made it very easy to create very pure materials, and a year later the transistor was invented. Once he gave him zone melting, it was just a matter of months. It hadn't been those guys, it had been somebody else. Not taking away that they were very bright to invent it, but once you had pure materials, some physicist was going to invent it in a very short time. So what did Bill Phan do? Well, I'm oversimplifying a bit, but basically it's the following. Suppose I want to make a really pure B. And let's suppose that this is a phase diagram because it's a very simple one to describe. I want to give you B that's as pure as you want it. How can I do that? Suppose I now take the liquid, this composition, but I start with not very pure at all. I drop it into the two-phase region. The first solid that comes out is much, much richer in solute, much purer in B than what I started with. So suppose I go just far enough into the two-phase region so I get a decent amount of this, and let's imagine I reach in with a spoon and I take it out. I've suddenly got a starting material that now has this composition. Let me take that starting material, reliquefy it, solidify it. Well, when it hits the two-phase region, the composition is purer still. So by just repeating this process, going just inside the two-phase region to create a solute-rich alpha, extracting the solute-rich alpha, and then repeating the process, I can make you an alpha phase that is as pure in B as I want to. You want 5 nines, I'll give you that. You want 7 nines, I'll give you that. Just this process. Well, Phan went a little bit further, and he developed a way to do this continuously by taking a bar and passing it through a furnace that would create a molten zone that would just travel along the bar and push the solute to one end. And it's done routinely these days. And that is, it was a continuous process that accomplishes basically this little process right here. And by just cycling through that solidification region and always extracting the stuff that is pure, you can make a B that is as pure as you want it to be. I can also make an A as pure as you want it to be. To do that, all I have to do is take out the alpha, throw it away, and keep the liquid. Because the liquid is constantly evolving toward the A side. So I can go either way with the zone melting process just repeating. And that's what happened. And that was the enabling technology that allowed the transistor and subsequently microelectronics to come into being. Question? Once you get below TA, you just have whatever alpha you have. But remember, if you cool all the way down to the solid line here, then the whole solution will have this composition again. As I go through the two-phase region, I go from a pure liquid at this composition to a pure solid at this composition. However, when I'm inside the two-phase region, I have a liquid and solid whose compositions are significantly different. So it's that separation that I use for zone melting and purification. Okay, the next one is the eutectic phase diagram. In terms of the free energy curves, this is really kind of simple. In this case, at high temperature, low temperature we have two phases, alpha and beta, therefore two free energy curves. So at low temperature, my situation looks something like this. The liquid phase free energy curve must be up here because it doesn't cut through at all. At high temperature, the liquid is below both the alpha and beta, so I'm pure liquid. in the intermediate region here, the liquid cuts the common tangent between alpha and beta, just like in the example I showed you a few slides ago, to give you a situation that looks like this. Now my common tangents are between alpha and liquid and beta and liquid, and my temperature would be above what we call the eutectic line here. You see, we start out with alpha, get an alpha plus liquid region, that's right here, then pure liquid, that's right here, then beta plus liquid, that's over here above x3, alpha below x1, alpha plus liquid between x1 and x2, liquid from x2 to x3, beta plus liquid from x3 to x4, and then finally pure beta. So that's going to happen as the liquid has cut through. But as we lower the temperature, the alpha-beta common tangent keeps coming down with respect to the liquid phase. Once the alpha-beta common tangent passes across the bottom of the liquid phase, the liquid no longer appears. And that's in the diagram right here, what we call the eutectic point. And that will generate this simple eutectic phase diagram. We have two solid phases down here, with a liquid up here. This, incidentally, is the simplest phase diagram you can possibly have when A and B have different crystal structures. Because if A and B have different crystal structures, there must be different terminal solutions. If there are two different terminal solutions, alpha and beta, there must be at least one two-phase region between them, because I can't go continuously from one to the other. So I must have at least this situation. Life can get much more complicated than that, as I showed you in the aluminum copper diagram, but it's got to be at least this complicated. So if I give you two materials that have different crystal structures, like lead and tin, lead and antimony, and I say, what is the simplest phase diagram they could possibly have? The answer is either the eutectic diagram or what we call a paratectic diagram, which is in the notes. I won't cover it in the lecture. That's just a case where the liquid phase intrudes over here somewhere on the left-hand side rather than between the two phases. Rather more complicated situation, but basically the same situation. So this is the simple eutectic diagram. Now, to finish up, I told you how we use the solid solution diagram, among other things, to do zone melting. You can do zone melting with a material that has eutectic structure as well if you want. Suppose I come over here. Suppose I want pure beta, and I'm over here. Well, I can get a pure B. I can do zone melting right in this region of the phase diagram and generate pure B. I can do zone melting in this region of the phase diagram and generate pure A. If I'm in this region of the diagram, there's no way to get pure A, because I can't get past the eutectic point. But let's now consider the different microstructures that we can generate from a material that has a eutectic diagram. If we solidify, as you did in the lead antimony laboratory, so that we maintain something pretty close to equilibrium, what are the microstructures we're going to generate? And I'll consider three cases. The first is X1, where we're over on the left side of the diagram. The second is, I'll talk about, is X3, where we pass right through the eutectic point. And the third is X2, where we pass through this two-phase region. If I were to go the other side of the eutectic over in the beta region, I get the same general microstructures. It would just be reversed. So let's start out here, solidifying X1. We solidify at composition X1 and maintain equilibrium. We hit this liquidus curve and begin to precipitate alpha. The alpha initially has the composition over here to the left-hand side. As I come through that two-phase region, the alpha becomes richer in solute and there's more of it, until I enter the one-phase region right here. And at that point, I'm 100% alpha, and here's the composition. And I might expect to see a microstructure look something like this, just equiact grains of alpha. Now let's suppose I continue down in temperature, and I exit the one-phase region as shown in the by the arrow here. What happens then? I'm coming out, so I now want to nucleate beta phase with this composition over here, almost pure B, way on the other side of this two-phase region. Well, within the alpha microstructure, I'm going to begin to form precipitates of beta phase. They may be in the interior of the grains, they may be in the grain boundaries, we'll discuss that a little bit later, but I will begin to form precipitates of the beta phase. So if I come down through here, I wind up with a microstructure that's going to look something like this. Grains of alpha, and in the grains of alpha, or in the boundaries, one or the other, I've got precipitates of beta. I'll see a precipitation decorated solution. Well, now suppose I whip over and come right down here, right through the eutectic composition. Then I get, if I cool slowly, a very interesting and rather different kind of microstructure, what we call a eutectic microstructure. You saw that in the lab. What I will end up with is grain-like colonies. And within the colonies, I will get bands of alpha and beta that alternate. Well, now why would that happen? If you look at what happens at the eutectic point, the reaction that occurs, if I cool right through that eutectic point, is what we call the eutectic reaction. The liquid transforms to a mixture of alpha and beta. The alpha and beta must have two characteristics. They must have compositions that are way apart from one another because they come from the opposite sides of this two-phase region. They must have mole fractions that are balanced so that the net composition of the alpha-beta mixture is just the eutectic composition. Well, how can that happen? The way that can happen in a kinetically suitable way, we'll return later in kinetics, is suppose I start forming, if I were to just form alpha because its composition is way over here, I'd dump all kinds of solute. The alpha could only grow a little bit before something would have to happen. Similarly, if I form beta, it sucks up all the solute. Therefore, a halo around that particle would be solute lean, and again, something would interfere with the growth. But if I can form them so they grow side by side, as the alpha grows, the solute that I dump is immediately picked up by the adjacent beta. As the beta grows, the solute that it sucks up is coming from the adjacent alphas, so I can move this interface along with very little diffusion, and all that diffusion is happening in the liquid phase where it's easy. So this eutectic microstructure is a common microstructure that we get from this eutectic reaction. Now suppose that I come down here in between the two. What I then get is a pseudo-eutectic. I get a bunch of what we call pro-eutectic alpha around eutectic colonies. Why? Come down at X2. Right here, at the solidus line, I begin to kick out alpha, which is very lean and solute. It's coming out from over here. As I continue to come down in temperature, I get more alpha phase, and its composition is evolving along this line so that it reaches eventually this point. But when the temperature reaches the eutectic line, I still have a significant fraction of liquid phase. So I have alpha of this composition, a significant fraction of liquid phase. The liquid phase is now exactly at the eutectic composition. So it undergoes eutectic solidification. So I have sequential reactions. I have the solidification of alpha, and then the residual liquid transforms into eutectic, something like that. And so I get microstructure looks like this. Here's my what we call pro-eutectic alpha because it formed in the alpha phase. And then I have eutectic colonies that finish up the liquid phase. Yeah.
Does this prevent dislocation lines from
We'll get to that later. Don't worry about the dislocation now. Worry about the microstructure. Okay. Let me just give you some quick examples. This is the eutectic. Here are examples of lamellar eutectic. This is a tin bismuth eutectic. You see it's not a perfect arrangement, but an essential arrangement of parallel plates, some irregularity. Incidentally, within these colonies, you tend to have two crystals. The interconnectivity is such that the tin is light phase, I'm pretty sure here. The tin is all the same crystal, and the bismuth is all the same crystal. They're just intergrown to form these eutectics. This is indium 3 silver. This is a little different because this is almost 50-50 tin bismuth, but this is silver, very, very rich in silver. So the indium, which is the light phase, is a little bit more dispersed. You don't get quite the same regularity. The indium is in the form of rod. In this case, you're growing plates. As you move away from a 50-50 composition, the minor phase tends to grow as rods rather than plates. And so here you see some of the rods are in the plane of view or close to it. Some of the rods are perpendicular to the plane of view, so they look like discrete particles. They're actually rods. They're just looking at you instead of sitting on the board. Well, we can control these microstructures, and we do in things like soldering operations, because this, in fact, is a lousy microstructure from the point of view of mechanical properties. Your biggest problem in a solder joint and a microelectronic device is thermal fatigue. You turn your device on, it gets hot. You turn it off, it gets cold. Differential thermal expansion means that the poor solder joints are going like this. So before long, one of your joints breaks, your device won't work anymore, unless you're an intelligent engineer and whack the hell out of it, in which case the surfaces come back together and it works again. And that's kind of common problem. This microstructure turns out to be very poor in that kind of cyclic fatigue, just because of these are big particles and complex in their relationship. So what we'd like to do is replace this with something that's very fine-grained, uniform. We can do that in the following way. Here's a lead tin, what we call divorce eutectic, tin bismuth, divorce eutectic. All I've done in this case is dramatically increase the solidification rate. I'm pulling the heat out of the system and making it solidify very quickly. This ordered structure for solidification is a very good structure for solidification, but you can imagine it takes some time for you to get this self-organization going properly. So if you can hit this really hard, you can prevent this from happening and end up with microstructures that look like this. In solder joints, these are the kind of microstructures we want. These are the kinds of things that we do. One of the biggest problems in the field of solder right now is that we're now using tin-rich solders. Well, let me go in further and I'll show you that. This is the silver tin system, which is not that far off what we're now using for lead-free solders. This is an asymmetric eutectic. Look, you've got the eutectic way over here. That means that in the eutectic phase, it's almost no tin. So you have just a little bit of tin sitting in the microstructure, sometimes in the form of long needles. Well, what I will start out with on Monday is I'll go back and just as an indication of how we use these diagrams, tell you how what we have to do to try and control these various microstructures. Okay, let's see then. Oh, for planning purposes, next Friday there will not be a class. I have to do an airplane crash inspection.